Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks for coming. It's my pleasure to introduce Sam Hasnoff. Sam's a PhD candidate at University of Toronto. He's actually no stranger to MSR. He was an intern with us back in 4 years ago, 2003, and he was an intern at MSRA at 2005. Sam has done a lot of interesting work. His master's thesis is actually on reconstruction of fire from images. So that's quite interesting. Since then, he's done a lot of other interesting work, and he's going to be talking about that right now.
Well, thank you very much, Singbing. So today I'm going to talk about the potential of variable aperture photography. And by that I mean capturing multiple photos just by manipulating the cameras on a standard digital camera. So I'm going to show that by combining these photos, we can use this information that's encoded in Defocus and achieve a variety of different goals. I want to say this is all this is joint work with my PhD supervisor, Kyros Koudelakos, at the University of Toronto. Now, although we have modern cameras that incorporate an impressive amount of engineering, in terms of their functionality, they're all actually pretty simple. All conventional cameras share a standard set of controls: exposure time, focus, and aperture. So without moving the camera to actually change the viewpoint, our basic options for photography are very limited, just to changing 3 controls. So for a fixed camera position then, every photo can be visualized as a point in this space of camera controls. But in spite of the seeming simplicity of this model, we still don't know all that can be accomplished just by taking photos with these controls and then combining multiple photos from within this space. In this talk, I'm going to talk about 3 different projects that fall in this domain, each of them addressing different goals. Now, by restricting ourselves to this domain, there are 2 main advantages. The first of which is that anyone with a digital camera has a potential to put these methods into potential practice. And the second advantage is that any theoretical advances from these methods could find application anywhere that conventional photographs are analyzed. So first I'm going to review the 3 basic camera controls. The simplest camera control is exposure time, and we know this manipulates the amount of time the shutter is held open, so slower exposure times allow the sensor to record more light and lead to these brighter images. Real cameras, we have to be careful, measure brightness with limited precision, so we have to record pixels, making care not to record pixels with extreme values, because these we lose basically all information. Next we have a focus setting control, which manipulates the distance of the in-focus region in the scene. Here we have a near distance in focus and a far distance in focus. Now the in-focus region, shown by these green rectangles, also known as the depth of field. And what this defines is the maximum, is the region where blur is acceptably in focus. In practice, we define this region of acceptable focus using some maximum blur level. It's shown here with the red zones. Within the depth of field, the scene is captured with perfect sharpness, but outside we see increasing levels of blur as we get further and further away from the depth of field. The last control is aperture, and this is the opening that allows light to enter the lens. Aperture is interesting because it has 2 different interconnected effects, the first of which is that it opens the lens more, so it opens more light, it allows more light into the sensor, leading to brighter images. But if we adjust the exposure time to give the same overall brightness, we can see there's a second effect as well, and that's reducing the depth of field, reducing the region that's in focus. Here we go from 3 faces to 1. So to summarize, just by manipulating basic camera controls, what we can obtain are different photos that are varying in terms of different brightness levels and also in terms of different defocus characteristics. So both brightness and defocus depend on 2 different camera settings each, but in different ways. Image brightness depends on exposure time and aperture setting, but these happen in a very simple way in terms of their combination. Defocus, on the other hand, depends on aperture and focus setting, but these are orthogonal controls. So while focus is changing where in the scene is in focus, aperture is controlling how much of the scene is in focus. So in this talk, I'm going to give 3 different projects that are all based on capturing different sets of conventional photos within this space, and they're all going to be closely related in the sense that they involve analyzing changes in aperture setting. I'll show that in each case, the information that's encoded in defocus can be used to achieve different goals. So in the first case, we have by manipulating both aperture and focus setting, capturing a large number of images, holding exposure time approximately constant, we're able to achieve 3D reconstruction at very high levels of detail. In the second case, I'll show that by using the one-button aperture bracketing feature that's built into many digital cameras, we can actually resynthesize new images within this space. And finally, I'm going to talk about our current work, which is about capturing photos with a given depth of field with the lowest possible exposure time. So on to the first method, our 3D reconstruction method. The motivation for this project comes from the fact that there are many common scenes for which obtaining 3D models is just beyond the state of the art. We have one important class of these scenes are scenes that have very high geometric complexity, like the wool, vegetation, and hair that you see here. Reconstructing these scenes is difficult for a few reasons. First of all, the very fine detail requires imaging them at high resolution. Secondly, the geometric complexity of these scenes means that changing viewpoint just a little bit drastically can change the occlusion relationships in the scene. And finally, these scenes can't even be represented in terms of smooth surfaces. But despite these challenges, we have today's digital cameras with resolutions up to 20 megapixels. So these cameras open the possibility of accurately reconstructing such scenes, with individual strands of hair, for example, being imaged at 1 or more pixels. So as a first step in this direction, I'm going to talk about a new technique that we call Confocal Stereo, and this is specifically designed to reconstruct scenes of very high geometric complexity. Our Confocal Stereo method is based on 3 ideas. The first and the most important one is that we can radiometrically correct the lens, calibrate the lens, so that under very mild assumptions under the scene radiance, we can say that the color and intensity of an in-focus point projecting to a single pixel will remain unchanged as we change the aperture setting. As you can see here, the in-focus points on the foreground strand of hair are staying about the same color. As we change the aperture setting, the background points are going to defocus and changing. To exploit this property for reconstruction, we vary the focus setting of the lens, and then for each focus setting, we capture a number of photos with different aperture settings. We then align all the images within the space, geometrically and radiometrically, to account for the distortions caused by real lenses. The third idea is that we can organize this data into a set of aperture-focused images, one for every pixel, that describes an individual pixel's appearance as focus and aperture are changing. We show in this representation computing the depth of the pixel is reduced to processing this aperture-focused image locally and finding the focus setting that best reproduces is most consistent with the Confocal Constancy property. Now, this builds on several lines of work. First of all, we have complex scene reconstruction methods, but these rely on particular generative models of what the scene is. Here we'd like to do very complex objects, but we don't want to assume any kind of prior knowledge of what the scene. Our work is really most closely related to shape from focus and shape from defocus techniques. But these methods use focus criteria that can only be applied to windows of pixels. And so they produce depth maps whose effective spatial resolution is much lower than sensor resolution. Here we'd like to increase the spatial detail as much as possible in the reconstructed depth maps by evaluating the focus at every single pixel individually. And this is of course a trade-off here because we capture a lot of images and many of these techniques use far fewer images than we do. And we're aware of only just one more technique that can recover depth estimates at sensor resolution using defocus, and this relies on using a camera and a projector which are aligned to the same axis and capturing a number of images. What we do instead is that we address this reconstruction problem using regular SLR lenses, and we analyze the defocus characteristics of those lenses. So to do so, we have to generalize some common notions about lens calibration in order to make this work for very high-res images. More specifically, given this A by F set of images over A aperture settings and F focus settings, our goal is to compute for every single pixel P what is the focus setting that causes the scene point projecting to P to be in best focus. Now to achieve this, we assume that the scene is viewed through an unknown general lens that can contain all kinds of different focusing elements. And this is a general black box case where we model the lens as redirecting incoming light rays to outgoing light rays. We assume this lens, though, satisfies 3 basic conditions. First of all, the aperture setting of the lens only determines which of the rays are blocked. It doesn't determine how the unblocked rays actually pass through the lens. Secondly, all the light entering the lens is either blocked by the aperture or passes without absorption. And finally, for any visible scene point, there's a focus setting that brings that point into perfect focus. So these 3 basic properties are satisfied by typical SLR lenses. For the scene, the key assumption is that when a point is in focus, the radiance within the cone for that scene, given by the largest aperture, is approximately constant. So this is much weaker, in fact, than standard Lambertian reflectance assumptions, because for the typical distances the points are away from the camera, this is only going to be a few degrees. Note that this assumption also implies that the cone does not intersect the scene elsewhere, but in practice it's still a good approximation for scenes with partial occlusion, where the occlusion does not significantly affect the average radiance over this cone. The last assumption, as in any defocus-based technique, we assume there's sufficient local appearance variation within the scene to be able to resolve changes in focus setting from in-focus and out-of-focus regions. So at the very heart of our approach is this simple observation that relates the appearance of a scene point over two different aperture settings. And in general, the pixel intensity at point's projection is proportional to the integral of the outgoing radiance at that point and the cone of the rays that reach that pixel. But when the radiance is approximately constant within this cone, this means that the pixel intensity is just proportional to 1, the cone's total solid angle, and 2, the point's average radiance. So in this case, the ratio of intensities for the same pixel at two different aperture settings becomes a scene-independent constant that depends only on the lens itself. And we call this the Confocal Constancy relation. It has several important features. First, it doesn't rely on any strong assumptions about the lens. Second of all, it's a necessary condition for focus, and so as such it leads to a focus measure that depends only on the measurements of a single pixel. It also doesn't require any assumptions about the appearance of the out-of-focus points, but we can see later that actually by generalizing this model, we can explain the entire AFI and lead to a focus criterion that's even better behaved. So confocal constancy tells us that to relate the pixel intensities of an in-focus point over those two aperture settings, all we need to know is this constant proportionality. We call the relative excellence of a point P, which is varying over pixel P and all different lens settings. So there are 4 general steps in this reconstruction method. First, we acquire a 2D set of images by varying aperture and focus. We align them all to a reference image. We build an AFI for every single pixel, and then independently we process every AFI to find the best in-focus setting for that pixel. In the confocal constancy case, this amounts to looking at the columns within this representation for which the variance is the lowest. This gives us an error metric. We'll see later, though, we can generalize what this means and find a confocal constancy metric more general to find an error function that fits the entire AFI.
Sam, you account for image noise because different settings of noise characteristics.
That's true. We have different exposure levels that are meant to compensate for general brightness. But beyond that, as far as noise goes, we're not doing anything specific. I want to talk mainly about the global structure of the AFI because this is the key basis for our method. You can see here that if the focus setting is at the narrowest aperture, we're going to approximate an ideal perspective camera where everything's visible and in focus. So the pixel color is supposed to be constant within this case. Now if you look at the widest aperture, the pixel color is actually going to vary the most within this range. What confocal constancy tells us is that the column of the AFI at the in-focus position is going to have constant color and intensity. So clearly we can use this to test a specific focus hypothesis. Are we in focus? By looking at the variations within the corresponding columns. But we can generalize this. The in-focus setting of a pixel constrains a lot more than one column of the AFI. That's because when the cone subtended by the aperture has a small angle, we can establish relationship along a curve within this space and say the amount of defocus will be the same for all these settings. In terms of the differential power of each patch, we can show they satisfy confocal constancy as well, and what this means is the pixel intensity will be approximately equal for two different cones that produce the same level of blur. That is, two different cones which subtend the same solid angle within the scene. Now in practice, we don't know the scene, so we quantify the blur using the diameter of this circle, assuming that the scene is aligned with the in-focus plane. What this allows us to do is to take our AFI and to partition into different regions, each of which should have equal levels of blur, and each of which should have thereby equal levels of color and intensity. So each focus hypothesis for a pixel gives us a different partition of the AFI into these equiblur regions. It gives us a very simple way to test whether a pixel is in focus or not. If our hypothesis is correct, the color in each of the equiblur regions is constant, so we can synthesize the least squares optimal AFI just by taking all of the pixels within each of those regions and averaging them. This gives us an error function, and by minimizing the error function, we can find which is the focus hypothesis which is most consistent with our AFI. Before we can actually apply these criteria for shape recovery, we have to align our input images and do so both geometrically and radiometrically. So we model the subpixel distortions that happen at high res, and when you change the focus setting, there are three main components here. The first is the standard magnification factor, which happens as you change the focus setting. Second, we have this quadratic radial distortion term, which also has a linear term related on the focus setting itself. And finally, we have a random global translation that changes from image to image and is based on such things as the camera shaking around, even on a tripod. So for very high-res images, this can be large, up to a pixel. Well, we estimate the deterministic parts of this scene using a fixed calibration pattern. We do this once in an offline step. And for the online random part, we do this using Lucas-Kanata image registration. What this means in practice is that we can reconstruct, is that we can align 16 megapixel images of the scene, and to do so with subpixel accuracy. For radiometric alignment, this amounts to computing the relative extents of the lens for every single pixel, and we do this in a very straightforward way by taking photos of an in-focus diffuse white plane and just dividing the intensity of each pixel in aperture setting by the intensity of the same pixel at the reference aperture. Now, this process implicitly accounts for vignetting, off-axis illumination, and various exposure levels that we might be taking without relying on an analytic lens model itself. In practice, what this lets us do is to radiometrically align images that are taken at different aperture settings within a couple of gray levels. Okay, to test our approach, we used a high-end consumer SLR camera with a wide aperture lens and a fixed focal length. We captured images across 13 different apertures and then 61 different focus settings. So our workspace amounted to actually a depth resolution of about 3 millimeters. Okay. I'll play that now. So the first data set was a scene we've been looking at all along, the wig with the artificial plants. And in these results, we're going to compare AFI model fitting method with a shape from focus method based on maximizing the variance within a small window. For the rest of the video, this top right image is going to cycle through the different widest aperture images so you can get a sense of how the shape is varying. And this is exactly the input that's used by 3x3 variants. Now, at a coarse level, you can see that both of the methods are accurately reconstructing the overall shape. However, the background pixels, which are outside of our workspace and are untextured, the estimation is really unreliable. Now we show this zoomed-in region of the scene, and you can see the direct application of Confocal Constancy to the columns of the AFI is not particularly useful. For other scenes, the ground truth data set that we specify later, for example, the Confocal Constancy actually performed relatively well. The issue is that in the Confocal Constancy case, most of the pixels have multiple modes, so a greedy pixel level method that we're showing is totally insufficient. So I should point out that all of our methods are shown at pixel level with no smoothing. On the other hand, our AFI model fitting leads to very detailed depth maps at the level of individual strands of hair. Variance, by contrast, you can see produces halos around the narrow structures and doesn't recover the foreground hairs as accurately.
Can you do the model bit? Have you considered, if you have another pixel next to you which has a farther away disparity or closer disparity, or depth, as looking at that when you do the model fit and saying there might be two modes that fit well, and then.
So our original method wasn't based on the AFI analysis at all. It was just based on the Confocal Constancy. And when there were multiple modes, to get results that were better than sort of the garbage that you saw before, that's exactly what we did. And it performed fairly well, but not nearly as well as the AFI model fitting. So I think you could go even further by using that kind of analysis. But I just want to present the single pixel level stuff here. Here I'm going to show that you can also do a basic kind of filtering and figure out which pixels are unstable, which pixels are uninformed, as in the totally textureless case. And we can do this just by detecting pixels whose peak of the focus measure is too broad. So this filtering can actually significantly help in the AFI model fitting case because it's so distinctive. In the 3x3 variance case, the filtering has little effect since the worst artifacts are just caused by bad modes in the first place. Now, confocal constancy, here we're going to show another region of the scene, and in fact it's hard to keep the scene stable. One of the hairs is flickering around in the foreground, and you can see even though there is a large range of depths, the AFI model fitting is doing fairly well in this scene and resolving this thin structure and doing so better than the 3x3 variants. Now there's another area of the scene here which is much smoother and has less texture, and spatially based methods like variants have a big advantage in this method in this sort of case because they assume smooth surface models and these methods are have their assumptions satisfied. But we showed that AFI model fitting, especially in the presence of filtering, can actually do fairly well in these kind of regions as well. We just have to filter out the outliers. So the last part, we're going to evaluate some quantitative accuracy. We did this by considering the scene, which was a box that was wrapped in some newsprint, and then we recovered the ground truth depth information by using a sub-millimeter 3D probe device. What we show is by the varying texture characteristics of this particular scene, it leads to outliers in both of these methods. But most of the reconstructed 3D points actually reconstruct. They agree very well with the ground truth, which is shown here as a blue underlined box. Now for a small region of the box, we can see the level of reconstruction accuracy even more clearly with the ground truth plane overlaid as a 3D mesh. The planar scene can actually be thought of as a best case for 3x3 variants, but even so, AFI model fitting performs at the same level or better in terms of accuracy and the number of outliers. Okay, so just to summarize the first part, we described a new technique called Confocal Stereo that computes depth individually at every single pixel, and it does so by analyzing pixel variations over both aperture and focus setting. The key open issues that we're kind of exploring right now are by taking occlusion into account in our shape computation, and also in robustly handling regions of the scene which have very low texture. The next project I'm going to describe lies at the very other end of the spectrum in terms of the number of input images needed, and I'll show that how we can exploit the aperture bracketing feature, which is a one-button operation on many digital cameras to allow refocusing and other effects in post-capture, all of this with increased dynamic range. So we know that standard camera controls like exposure time, focus, and aperture give us flexibility to the photographer, but once a photo is taken, the settings cannot be modified. What we'd like is the ability to capture a set of input photos and then afterwards use our input to synthesize a new photo within this space. Now an obvious approach is to use brute force sampling, as in the input for the previous confocal stereo, but capturing a dense set of 2D or 3D points like this is not always practical. Now, if we could do this and synthesize any new image within this space, it would give us the possibility of refocusing, of changing the depth of field, or presenting results in higher dynamic range. So here I'll show that by using aperture bracketing, by varying aperture alone and holding all other settings fixed, we can capture a small number of photos, but still greatly increase the flexibility within the space. From functional terms, our method can be thought of as a generalization of high dynamic range imaging, in which images with different exposure levels are combined to give detail across a range of different brightnesses. Now this method's become recently very popular to amateur photographers and requires just a tripod and some simple software. So in our aperture bracketing case, we use the same number of input images, and we have a sequence of images whose brightness varies in much the same way. But by analyzing how defocus varies across the sequence, aperture bracketing lets us recover not only the in-focus HDR image, but also an approximate depth map. Although this requires significantly more processing, the richer representation of the in-focus scene radiance plus the depth allows us to synthesize new images, for example, refocused at different depths, all in a high dynamic range. Another practical advantage is that many digital cameras, they already have an aperture bracketing mode built in. So variable aperture sequences of this form that have 3 or 5 images can be captured using a single button press. We pose the aperture bracketing approach using an image restoration framework, where the goal is to determine the scene representation that best accounts for the input images. And conceptually we do this by inverting the image formation model. Because aperture simultaneously affects image brightness and defocus, inverting the image formation model means that we've effectively decoupled all possible camera controls. This is a great strength of our method, but it also leads to a difficult computational problem. Because brightness and defocus are so connected in the input, existing methods for HDR and defocus don't apply. The main key to the success of our approach is our formulation of a layer-based image formation model, which is both computationally efficient and carefully models defocus at occlusion boundaries. This lets us accurately account for the input images, even at depth discontinuities, while still being able to invert the model tractably. So while layer-based representations are common in computer vision and graphics, our model is actually the first of its kind to handle occlusions for general layer configurations and do so in an efficient way in the presence of defocus. Now there are a related set of techniques come from the shape and defocus literature, and these are techniques that compute shape and defocus using restoration. The output of these techniques is an in-focus radiance and a depth map, just like in our case, which theoretically permits post-capture resynthesis. But these methods use an additive image formation model, which leads to very severe artifacts at depth discontinuities. In a similar way, we have image-based refocusing techniques that are designed for refocusing, but don't handle occlusion either. Now, very recently, several new systems have been proposed for doing post-capture resynthesis, although all of these involve specialized hardware. One advantage of these methods is they only rely on capturing a single generalized image. We can say, broadly speaking, though, these new designs complement our analysis, and we can benefit from the features they offer. So a key aspect of our approach is the layer image formation model that describes how we can defocus the scene and create an image while taking occlusion into account. Our model builds on the standard thin lens model, which is especially simple for a single layered scene. Now for a general multi-layered scene, we can determine the intensity and the color of a defocused pixel just by back projecting the appropriate cone into the scene, taking occlusion into account, and then integrating radiance. So here we see that layer 1's contribution to the pixel only involves radiance from the lower region of the cone, whereas the top region is actually blocked by the scene. The problem is that in computing defocused image in this way, it can be very computationally expensive. This is because the relative contributions of the different layer will vary across the image, and the layers can combine in complex ways according to the arbitrary geometry of the occlusion boundaries. To address this problem, we propose an approximate model for layered defocus that's designed to maintain the simplicity of the one image case while accurately modeling occlusion effects. The key idea here is to defocus each layer independently, but to weight each layer's contribution using the fraction of the cone that reaches it. The advantage is that both of these components can be computed very efficiently using standard image convolution, as in the single layer case. Now this approximation will be accurate when the mean radiance of the occluded and the unoccluded regions of the scene are similar. This is less likely to hold if the unoccluded fraction of the scene is large, but in this case the contribution of the occluded radiance will be relatively insignificant anyway. So this is a good approximation in practice. More concretely, we can say that our model for layer defocus leads to a general compositing operation that extends these previous methods. First, each layer and its corresponding alpha mat are blurred independently according to the blur diameter associated with its depth. Second of all, each blurred layer is modulated by a second mat on the right side that represents the cumulative effect of occlusion for all the layers that are in front of that scene. And finally, we take the result and we sum over all the layers. I should say that an important feature of this method is that the compositing equations we get lead to very simple analytic gradients that can be computed efficiently and make inverting the model very tractable. But to make the formulation even simpler, what we assume is that the entire scene can be represented using a single all-in-focus high dynamic range radiance map. Now in this kind of setting, the scenes divide into layers using a hard segmentation where each layer is a binary alpha mat that selects certain pixels in the all-in-focus image. We implicitly assume that the all-in-focus radiance is sufficient to describe the occluded regions in the scene as well. In practice, we specify the occluded parts by extending the unoccluded parts of the layers by using in-painting methods. Otherwise, the exact same compositing model as before is applying. We blur the layers independently, we modulate by cumulative occlusion, and then we sum. So the complete multi-layer scene model can now be represented using three components: the in-focus scene radiance, a segmentation of the scene into layers, and the per-layer blur diameters. To compare our layer defocus model against the standard alternative, we use the results of our method to resynthesize a scene with an extrapolated aperture, We can see that our method generates more realistic results at occlusion boundaries. Now for the standard additive model of defocus, the foreground and the foreground layer and the background layer get blended in an indiscriminate way that creates this distracting halos around the side. Note that even though the layer segmentation of our scene is not estimated perfectly, as shown by the depth map, our image formation model still leads to a synthesized image that's visually realistic. Now, given the scene description and the image formation model, we're finally in a position to formalize what we mean by computing the image restoration problem, and that's determining the scene that best accounts for the input images. So as usual, we formulate this as a minimization of an objective function, and there's two terms. First, we have a least squares pixel-wise error term that penalizes scene models that don't reproduce the input images. And second, we have a regularization term that will reward piecewise smooth scene radiance, but in a way that extends the usual total variation penalty to handle large dynamic range scenes. And to optimize the objective, we use a very simple minimization scheme. The core approach is to alternately optimize with respect to both the in-focus radiance and the per-layer blur levels. To do so, we take steps using the conjugate gradient method, which is very simple because the analytic structure of the gradients is very simple themselves. We also periodically refine the layer assignments, and to do so, we currently use a very naive heuristic that reassigns layer labels for whatever pixels have a high error and test that out. In addition, we also re-estimate the ordering of the layers. We do so using a brute force approach. So for K layers, each of which can lie in front of or behind the in-focus plane, we have to test on order of 2 to the K orderings that are consistent with the per-layer blur levels.
How do you initialize the layers?
This is how we initialize the layers. The last part of the method is how to initialize this. And to determine the number of layers and the layer assignments themselves and the per-layer blur diameters, what we do is basically a simple shape from defocus method. And we explicitly test various defocus hypotheses for consistency by incrementally blurring and brightening the input images. The results are then refined in a Markov random field framework where we use graph cut method to bias our estimates again towards piecewise smoothness. We also have to initialize the in-focus radiance, and we do so at every pixel on a pixel level just by selecting that pixel from the image with the narrowest aperture for which the signal-to-noise ratio is below a certain threshold. Now, I'll show some results. For all these results with real sequences, we captured images with a digital camera fixed on a tripod. The middle aperture was set to f4, plus or minus 2 stops, and this is equivalent to exposure levels of 1, 4, and 16 in relative terms. I'll show the results on downsampled versions of the images. The first sequence we captured outdoors, and it's composed of 3 distinct layers. A darker foreground dumpster layer is actually the one that's almost in focus. So first I'm going to show a video that synthesizes images of the scene with varying aperture, but without changing the focus setting or the exposure time. And you can see how image brightness and background defocus both increase with the simulated aperture increase. And this corresponds to interpolating over the input with some extrapolation too, shown as the red. Next is we're going to show a video where the aperture is simulated to be very narrow, so the entire scene is within focus. So here we're just simulating variance and exposure time. And the purpose of this is to inspect the quality of the all-in-focus high dynamic range image. The last result for the scene shows refocusing. And we can refocus this in high dynamic range using just a very simple operator to compress the dynamic range of the scene down to the display. So we can see here how each of the 3 layers that are indicated by the ticks on the middle focus bar are coming in and out of focus. And you can see that defocus is visually realistic here, even at the layer boundaries. Now the next sequence was captured indoors, and it's a portrait that's severely backlit from a window. The subject here was nearly in focus, and it's very dark compared to the background buildings. Also there's a very, very dark defocused chair that's in the foreground. Now the refocusing results for this scene are generally very realistic too, but because the foreground chair was underexposed even in the very widest image, we can see some artifacts that happen at the boundary of this layer that are due to posterization. Now just to get a sense of the method's limitations, I'll illustrate a failure case as well. And this is a miniature scene that was captured with macro photography. And it's very challenging because the range of defocus levels is very high, defocus is severe, and the object's depths don't decompose very easily into frontal parallel layers. So here we can see as we're varying aperture setting, which is normally very easy to determine good results in this case, we have tearing artifacts and brightening contrast around the tea leaf that's on the side And this is partially caused by the bad layers, but it's also caused by our in-painting method. And here's the focusing results for this scene, which also creates artifacts which are objectionable at the layer boundaries, but because this is image-based, within part of the layers themselves, things look fairly realistic. We're also going to show our method on a synthetic data set that's composed of the Lena image that we artificially exposed to have different brightness levels. And in this case, we can see the quality of the reconstruction is excellent. The hardest part of these scenes are the scenes which are both defocused and which are dark. And in this case, we have to reconstruct a sharp image, but to do so, we actually have to deconvolve and restore the image, which leads to a loss of detail. Here you can see that we have sharpness restored in this lower right region of the corner. And also throughout the scene, as we see in this error map, we have the denoising effect because we've added actually synthetic noise to our ground truth to make this a more complicated case. Now in refocusing, we have the 3 horizontal bands that correspond to layers. As we manipulate the focus setting, we can see that this is reproducing something realistic as well. So in summary of this part, we've shown how aperture bracketing, while a simple control, it lets us attain our goal of realistic post-capture resynthesis over a wide range of different aperture, focus, and exposure settings. The future work here is relaxing the restriction that the subject remains fixed, and this is possible maybe by integrating a per-layer motion analysis. We'd also like to improve the performance for more complicated scenes, which can't be represented very well using frontal parallel layers. Now, in the last part of the talk, I just want to talk about some current work very briefly on light-efficient photography that I'm excited about, and the goal is to capture photos with a given depth of field in the least amount of time. Our method involves capturing focal stacks, which are images with varying focus setting, and analyzing how do we choose a set of focus and aperture settings that span the depth of field of interest and do so in the least total exposure time. So just some initial results. This is work in progress. Suppose we're interested in a certain range of depths, and we'd like to capture an image that has that depth of field. So here we'd like the depths for the foreground region and also the background region behind the pillars to be in focus. Usual approach is to focus within the middle of this range, reduce the aperture as needed, and take a single photo. Now we can always do this. We can always reduce the aperture until the blur level over the depth range is acceptable, because in the limit, for the pinhole case, the entire scene will be in focus. But we ask the following question: what's more efficient in terms of total exposure time? Capturing the depth of field with a single image like that, or alternatively, dividing the depth of field into 2 intervals, capturing two different images, and then combining detail from each of the depth of fields. The 2-image approach, each image is actually focused differently, and the depth of field for a particular subinterval corresponds to the near part of the scene on the left and the far part of the scene on the right. So you should notice that because each interval is smaller than the original depth of field, we can obtain acceptable focus in each image by using larger apertures than before. But the question remains, in which case is the total exposure time lower? The single narrow aperture photo or 2 wider aperture photos? Well, as it turns out, in the 2-photo approach, we're almost twice as efficient in terms of total exposure time. And in this example, we need 2 seconds to span the depth of field in the 1-image narrow aperture case, but a total of just 1 second in the 2-photo approach. To see why this is the case, by dividing the depth of field in 2, this corresponds roughly to doubling the aperture diameter. But an aperture with double the diameter has 4 times the area, and so it gathers 4 times the light. And so to achieve the same exposure level as the narrow aperture image, for the 2-image case, we reduce the exposure time by a factor of 4. And then when we put these factors together, we achieve our overall 2 times speed up. Now this idea can be formalized, and we can show that for any depth of field whatsoever, capturing 2 wide aperture photos spanning the depth of field requires less total exposure time than a single narrow aperture photo. Our proof is simple and non-constructive, and just relies on a little calculus. So perhaps counterintuitively, by applying this result recursively to the intervals, we can keep dividing and becoming more and more light efficient until we reach some kind of limit that's imposed by the maximum aperture size of the lens. So what this says is that a dense focal stack that consists of a large number of wide aperture images with varying focus setting can actually be captured in less total exposure time than a single image with an equivalent depth of field. But there's another advantage. The focal stack representation also encodes depth information according to its defocus. So in addition to being more light efficient, the focal stack also gives us depth information, essentially for free. We could take our analysis further and show that for all physically plausible lens designs, the optimal division of the depth of field has a particularly simple form. We get the lowest possible total exposure time when the depth of field is divided into intervals that correspond to equal apertures. And this holds even for the general K-image focal stack case. We show an example here where the depth of field goes from 5 meters to infinity, and we'll divide it into 5 intervals corresponding to equal apertures. So it turns out that performing the analysis on the image side of the camera as opposed to the scene side of the camera, we can derive a very simple analytic formula that tells us where the equal aperture depth of field interval should be located. Now that we know the optimal way to divide the depth of field into K intervals, we can analyze what happens to total exposure time as we increase K. So our simulation here shows that total exposure time is going to fall off almost perfectly according to 1 over K. On the right, the red zone indicates that there's the largest aperture of the lens, which limits how far we can possibly subdivide the depth of field efficiently. Now in this example, capturing the full depth of field with a photo requires an f/22 stop on the lens, and when we're stopped down this far, it takes 1.5 seconds to capture the image. But using an f1.2 aperture requires 19 photos. We can span the depth of field within this range, but requires a total exposure time of only 80 milliseconds. So capturing dense focal stacks in this way, they lead to a massive reduction in total exposure time, theoretically at least. For many cameras, the overhead that's involved in capturing multi-aperture sequences can be significant. So for this particular camera, this is the 1DS, we require at least 220 milliseconds to capture an image. So it shows here how the total capture time is dominated by overhead beyond the first few number of images. So this changes our strategy. Instead of capturing 19 photos with the widest aperture, it's most efficient in terms of time to capture only 3 photos. But note here we can still capture a 6-image focal stack, and we can do so in less original time than it took to capture a single image. So we've reduced time and we can have depth information at the same time. Now for this to become practical and just a drop-in replacement for standard photography where we use a narrow aperture, long exposure image, we need a practical way to capture the focal stack first of all, and also to be able to synthesize the composites we need. To capture the focal stacks, our main approach has been to experiment with focus bracketing, which is a feature that's appearing on digital cameras where you can capture 3 differently focused images or 5 differently focused images with a single button press. We've also experimented with some unauthorized firmware that allows more generic programmable camera control on certain cameras with a Canon Digic 2 chip. And finally, we've also, for the previous stuff in Confocal Stereo, we were doing some motorized devices that will directly manipulate the focus ring on a digital SLR. Given this focal stack, we just exploit previous methods that are based on graph cuts to synthesize the composite. And these methods generally yield composites of very high quality with few artifacts. Looking ahead, though, more generally, we're interested in using light efficiency as a basis for comparison that would unify the analysis of a very wide set of passive 3D reconstruction methods. So in general, given a fixed time budget, how should we best collect photos, or how should we best redesign our imaging systems that would allow us to capture the most accurate 3D reconstruction? And to illustrate the principle of light efficiency as a measure of comparison, consider some recent methods that are based on using a coded aperture that blocks 50% of the light. So 3D results from this method are impressive given the fact that they just use a single image, but mainly these 3D results have been compared against using a single image uncoded case. What light efficiency tells us is that this comparison isn't fair, and this is because in the same exposure time we could have captured 2 different images with a full uncoded aperture, and to do so with different focus settings. So the basis of real comparison should be between this coded aperture case and something that would also involve incorporating the reasoning that we could capture about changes in defocus in the 2-image situation. So to summarize this, we've shown that the desired depth of field can be captured much more quickly by taking multiple photos with a larger aperture, and more quickly even in practical cases. But in fact, the time that we save from light-efficient imaging can be spent in other ways. We don't just have to save time, we could also use this time to reduce the noise level by taking longer exposures, or obtaining additional depth of field from before by capturing more photos or by using narrower apertures. And although the main motivation for capturing these photo stacks is to capture the same depth of field as the narrow aperture image in less time, the focal stack also has the important benefit that we get depth for free. We've just begun implementing this in real cameras. so I don't have some images to show you. But our first results show that this could actually be valuable in everyday cameras in terms of both having savings in terms of total exposure time and also in terms of depth and good composites. Another current thrust of this current work is exploring the trade-off between the noise level and the number of images within the focal stack. So by accepting a lower exposure level and therefore a higher level of noise, we capture more densely sampled focal stacks, and this may be preferable in some situations than a sparser but less noisy sampling. So, as we've seen, despite the seemingly restrictive domain of variable aperture photography, by identifying the right structure within the space of photos, we can use this framework to achieve gains in 3D reconstruction, in resynthesis, and in speed of capture. Now, some of these techniques have the potential to be applied immediately, but the lessons learned from this from conventional cameras also have the power to inform future and more sophisticated camera designs. Of course, these projects are not the final word on variable aperture photography, and in the future I'm interested in exploring new aspects of this domain, as well as a more general capture scenarios that involve viewpoint changes as well. So thank you for your attention, and be happy to take any kind of questions.
Any other questions? Mike?
Have you considered a form of coded aperture using an annular ring instead of a stop?
Yeah, that's interesting. So in analyzing the Confocal Stereo case, one of the questions I was looking at is whether it's possible to reproduce the entire light field, is whether we could use the output from any set of photos of different apertures and focus settings to reconstruct what a given ray in that space is. And what it amounts to in terms of the analysis is the information we have is exactly a set of annular aperture photos. By considering the difference between any two successive aperture images, that's what we have. So in terms of your question, which part of this were you thinking about? The confocal case?
Example, you're looking at reducing to the minimum depth of field, and you would get even a shallower depth of field by excluding the center of the lens using an annular ring aperture.
So using an annular ring aperture, we're increasing the depth of field. There's a range of images which can, and this is similar to the coded case and also some of the work on wavefront coding where you're actually manipulating.
It's easier to implement mechanically in a lens.
As opposed to changing focus.
Well, as opposed to rearranging the coding aperture, just to have an angular ring, essentially the inverse of a field stop.
Yeah, these are, experimentally I'm not sure how this would turn out. These are both methods which are along the same kind of lines. And they fall into the category of basically engineering your point spread function to have some coded information and to tell you some more information essentially about high frequency content. So there are a number of methods that are out there right now. If I show this one, right? So on the in the lower left-hand side of this, here, I've collected sort of a description of these methods that use coding within the capture space right now, and they're all based on the same kind of principles. Nice.
In the AI5 method, I didn't really get a sense for how much varying the aperture was buying you. For example, if you had captured half the number of apertures but double the number of focus
That's right.
settings you
Right.
set. What's the trade-off there?
So I captured as many as I had patience for when I did these experiments. The real way of looking at this is in fact the resolution for different apertures should be different. So when using the widest aperture, you should capture more focus settings. If you're using the narrowest aperture possible, maybe we only need one or two focus settings. Sort of this related question of how many apertures you need. Well, apertures that are wider are more informative. We've done some sort of initial experiments. You can see there's a journal submission for IGCV that's on my website that also gives just some initial sort of comparison of how the error falls off as how the error increases as we reduce the number of apertures. But a more systematic scheme for choosing which apertures are really the most informative, if you had a budget of just 4 apertures, or again, this light efficiency case, some of the apertures are faster and more useful in that sense. That's an open question.
When you're doing the light efficient photography, and varying the depth of focus, are you limited by the time to capture the images to the memory, or by the mechanical time to focus?
In practice with most of the cameras I've been looking at, the bottleneck is writing to memory. The way that these cameras focus is generally they have this with the different technologies, but some ultrasonic ring motor which can focus very quickly. If you know the focus motor position to go to, and you have access to the API somehow, and you can say go to focus motor position and so on, I can do that very fast. But I mean, in general, writing to disk is going to be higher than that. Memory's getting faster, but I assume that if you have to take if you're narrow aperture exposure, if there's enough light in the scene that even your narrow aperture exposure takes 100th of a second, you're not going to be able to divide this and take 10 photos in 1,000th of a second each, and also write that to memory. So the application of this is there's going to be more of a gain, especially in situations where there's less light. So time is of the essence.
Any other questions? No, let's thank Sam once more.